Are there any questions before I begin? Okay. Well, so um, there's two pages for today. The first page is all about this idea of area between curves. So I can at least explain conceptually what this is. So area between curves. So usually what you'll do is you'll have a function on top, call it f of x, and you'll have some function on the bottom, maybe like that, call that g of x. And then the area you're trying to compute would be in red, and it would have like some definitive endpoints, a and b. So from something that looks like that, you could say, you could then define an integral that will compute for you the area. And so this integral would run from a to b if we integrate with respect to x, and it'll be the top function minus the bottom function. It's pretty intuitive that this is the thing that would work, right? So yeah, that's how we compute area between curves. And if instead your functions were defined in terms of y instead of x, then it's just kind of the same thing except tilted sideways. And then in 5 we see some additional thing that can happen to it, but conceptually this is all we really need to discuss. So with that, let's just go ahead and do 3. So I would start by drawing this, because otherwise I can't really tell too much without drawing it. I feel like it's kind of necessary to. And one thing I know is I'm gonna need to plug e into, or well, actually not into there. We have 1 over x, so we know roughly what that shape looks like. We have this point, and then we sort of have like this kind of sloping thing that happens. And like if e is over here, then we know that like this is 1 over e as a result. The bounds y equals 1 and x is equal to e end up sort of boxing out the region for us. So the region that we end up integrating is the part that's in blue. Okay, and so you can see that the top function is going to be the function y equals 1. The bottom function is the 1 over x. And the limits for the integral are going to go from 1 to e. So it ends up being 1 to e dx, and it's 1 minus 1 over x. So you just have to compute this integral, and that's pretty easy to do. So ln absolute value of x. The absolute value in this case, it kind of goes away because these values that we're looking at are both positive. All right, so e plus 1 minus 1 plus 0. Okay, so you end up with wait a sec, something. Oh, this is a minus, which is why this is a minus. Yeah. So you end up with e minus 2. Okay, so that's pretty straightforward. Number 4. Yeah, so for 4 we have to draw things kind of sideways, since our perspective is now focused on, well, doing things with respect to the y-axis. So the curve given by x is y squared. That's the standard parabola, but sideways. So you can just sketch that. And then this x minus y squared is like you have a downward facing parabola starting off at 8. You know it's downward because of the negative, but then you tilt that sideways as well because we're viewing everything differently. Or you could imagine like that you're plugging in values for y, and then plugging in y equals 0 is going to give you an x value of 8. So you know that like that's the peak of the parabola. I'm trying to find my cursor. There we go. So at 8 it opens, and then it just sort of goes downward like that. And so the region is like this. I'm trying to shade it in a particular sense that helps me to see like what the integral that we would set up would be. Okay, so from this we know it's going to be 8 minus y squared minus y squared dy. We know that the top function, top in this perspective, is the function that is further away from the y-axis. So it's going to be the 8 minus y squared, and the bottom function is the y squared. So that's the order of the subtractions that we do. And then the other thing we need to know is where are these cutoffs? And I drew this kind of poorly because it's actually supposed to be symmetric. The way that we would figure out where these two curves intersect is we would set the two functions equal to each other and solve. Right. So the fact that they intersect means that this first function should equal the second function. And then we just solve this algebraically. So this is saying that 8 is equal to y squared, which means that y squared is equal to 4, which means that y is equal to plus or minus 2. So visually, this is saying that the first intersection point happens at 2, and then the second intersection happens at -2. And so this will end up being an integral evaluated from -2 to 2. Okay. Yeah, integrating this is also not so bad. So combined, this is -2y squared. Then you would integrate that, which would give you a y cubed over 3. So 2 over 3y cubed. And then you end up evaluating this from -2 to 2. Okay. I'm going to just cut out the calculation work. You can fill that in. 64 over 3. Like this one you can actually do by hand. I just feel like writing it down. Okay. But 5 is where the calculation work is actually rather terrible. And that one I will suppress that as well, but you'll have to at least write a little bit more. Okay. For 5, it's a little bit bothersome to work with because actually this cubic, the way it's given, this cubic is not factorable, but the difference is factorable because you know that the curves actually intersect perfectly at these x values. So the thing is, you still need some information about how these functions kind of operate. So as a very rough sketch of what this looks like, you've got a cubic, and then you have a line, and this line is going to cut it through like this, roughly speaking. And the intersection points happen at 1, 2, and 4. But the important thing about the shape of this is actually to get which function is on top and which function is on the bottom. Because if you were to cut it like differently, or if things were positioned kind of differently, you might have the regions, the top and bottom functions for the regions be a bit different. Because it's shaped like this, you know that in this region from x is 1 to x is 2, the top function is the cubic, the bottom function is the line. And then from the region 2 to 4, top function is line, bottom function is cubic. So you end up flipping the which function is on top, which function on the bottom. That tells you that actually the way to that you need to set up two integrals in order to calculate this correctly. So you need to calculate. So you need to actually split it into two different integrals. Split it at 2 because that's where the order of the functions reverses. So the first integral, well, it's x cubed minus 7x squared plus 12x minus 3. And then you would subtract off the line. So minus 5 minus 2x. which, I mean, yeah, I didn't want to do this thing by hand, so like um I just plugged it into a calculator. But for showing your work, you really should do it by hand. Okay, so, and I would say like you know how to do it. Um, it you should know how to do it. If you have questions, you can ask. But like this is just a polynomial, so it's reverse power rule. 2 to 4. The order of the subtractions is the opposite. So you start with the line, you subtract off the cubic, and then you calculate that integral. And so you end up with these two different areas. You have the two areas. That'll give you the area bounded by the curves. Okay. Well, but what I'll do is I'll at least give you what the values should be when you actually compute these two areas. So, or these two integrals. So the first integral, you'll get the value 5/12, and the second integral, you'll get the value 8/3, which will give you a total answer of 37/12. Okay. And I'll leave it to you to fill in all the work necessary to actually get these two numbers. Okay, it's just a calculation. It's a bit not complicated, just tedious. Tedious is the word I would use for that. Okay. Right. So, right, next we're talking about the average value of a function. All right. So what I want to do is I want to explain this concept by relating it to average value that you are already familiar with. Okay. So because when you look up like what this means, average value of a function on a domain, like there's a formula that describes it. But really the thing is that like this formula should just make sense. Like you don't have to think of it as memorizing. It should be something you can kind of reconstruct. It's always nice when you can just reconstruct the formula because that means you're not really like using any mental space. So yeah. So what I want to contrast this is like so I want to contrast the discrete case from the continuous case. And the thing is that the discrete case you already know about. This is something that you call the mean. Okay, sometimes it's called the arithmetic mean. The idea is suppose you're given a bunch of different numbers. Suppose you're given x1, x2, dot 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 up to xn, given n different numbers, and you're asked to take the average of these numbers. What does that involve? Well, that involves summing up all of the numbers. So one way you could write that is say a sigma notation, sum up all the xi's, and then you divide by how many values there are. And in fact, this also has like a notation to it. You can sometimes see this written as x bar, right? The bar means it's the mean, the average value of all of these of all these x's, right? So you're familiar already with what it means to take the average of if you have like discretely many like values, but contrast with the continuous setting. In the continuous setting, you don't have discrete values. You have a function, and you have like a set of values from an entire domain of like an interval. So, well, it turns out that what you do is something very similar. And the formula is like this. So suppose you're trying to take the average value of along the interval a to b of the function f of x. So I'm going to spell it out. Average value of f of x on the interval from a to b. So The formula you'll see is this. And the thing is that structurally, this is just this, except converted over to being in the continuous setting. See this summation of xi's, summing up all the xi's, that's what this integral is doing. It's adding together all the different values. Right? That's essentially what the integral is doing. And then this dividing by n, dividing by how many numbers you're averaging. Well, the thing that makes sense in the continuous setting is dividing by the length of the integral, dividing by this b minus a length. And so it kind of makes sense that this formula describes the average value of this function, right? It's just converting over. Okay. So yeah, keep that formula in mind. We're going to be using it for part 6. So we want to find the average value of this function g on this interval from 0 to 2 pi. So by that formula, well, you have to divide by the length that you're integrating over. You integrate over that length. And what are you integrating? You're integrating the function that you're trying to take the average value of. Plus e to the x over pi dx. Okay, so this will calculate the average value. Okay, and so we just go ahead and compute this integral now. So integrating that, let's see, this is going to be minus 2 cosine of x. And I want to say something about this exponential. Okay, so in the previous half of the homework, we would have treated this as a u substitution problem because, well, the inner function is this x over pi. Like you would relate this to e to the u using u is equal to x divided by pi, go through u sub. But like the thing is that this kind of u sub is so simple that you should actually be able to do it without running through the u sub process. You should be able to do it by just like kind of guessing what the core of the function is and then adjusting by a scale factor. Like it's so simple that you should be able to avoid it using the u sub properly. So the guess for like what this integrating this would be, it would be this function, right? You know that the exponential is going to stick around. You know that this inner function is going to stay. The thing is that happens is that this is off by a factor because you know that when you take the derivative of this guy, chain rule is going to make something pop out. So it won't give you this precisely. It'll actually give you a 1 over pi will pop out. And the idea is you want to cancel that 1 over pi. Okay, that pops out from chain rule. So how do we cancel that 1 over pi? Well, we multiply by pi. That will cancel out this extra scale factor and make it so that the derivative will match this precisely. Okay, so this is the way that you kind of you should think about it in order to avoid such simple u substitution. So this really is just a mental thing you can calculate easily. All right, so that is the antiderivative. We then evaluate. And there's one other clever calculation thing that we can do here, which is instead of evaluating piece by piece, you can kind of tell that this term is going to disappear. It's going to go to 0. And the reason, so instead of evaluating both terms, what we can do is just split that evaluation over the terms individually. And note that evaluating the cosine at 2 pi and at 0, well, those are the same angle, actually. So it's like you're going to subtract a number from itself. You're going to end up at 0. All right, and so the only thing that's left is now the evaluation of the other term, which is pretty easy to work with as well. So e squared, then you subtract off evaluation at 0. That's going to give you e to the 0, which is 1. So you end up with pi. And you see that pi is going to cancel. So we can cancel off this pi. And so the answer that you get is 1/2 e squared minus 1. It's the simplest way you can write that. Okay. So any questions on that problem? There's a bit of explanation that I had to give. So just want to make sure I didn't lose anybody. No? Okay, great. Yeah. So 7 is pretty much just a dressed up version of 6. So it's asking for average, the average value. It's an average value kind of problem again. It's just instead things are using like velocities and such. All right. So 2 p.m. and 4 p.m. those are the values that define the interval we integrate over. So you know that it's going to be plugging into the formula. It's going to be 4 minus 2 integral from 2 to 4. And what are we taking the average of? The velocity function. So this 40 plus 100 over t plus 1 dt. This will calculate average velocity. And so maybe I should say average velocity is going to equal whatever this calculation will give us. Okay. And then we just calculate this integral. Well, 40 is easy to integrate. And this guy, this 100 over t plus 1. So if I were to show all the u sub type of steps, like the thing is that I would relate that function to 100 over x. Right? When you just see a variable to the first power, that plus 1 is kind of like you can almost disregard it. That's a very easy u sub to do, right? Just like in number 6, that this was an easy u sub to this is an easy u sub to. So easy you should not even do it. You should be able to do it mentally without actually performing the u sub. You know that it's going to behave like this, so you know what the what your guess for the integral or the antiderivative should be. It should be 100 ln, and then the thing that is in the denominator, so t plus 1. And in this case, if you just think about taking the derivative of that, imagine that those aren't absolute values, but those are parentheses, you do get back this exactly. So great. Right. The only time when you wouldn't is if you have a multiplicative factor in front of the t, in which case you then divide by that thing that pops out from J null. So yeah, here this was very nice and easy. Where's my cursor? Okay. And then we evaluate this, right, from 2 to 4. Okay. Plugging at 4, 160 plus 100 ln of 5, and then plugging in at 2, we'll have minus 80, and we can also say minus 100 ln of 3. Okay, the reason I'm writing it this way is because I want to explain the next step in the calculation. So 160 minus 80 is easy, but this ln of 5 minus ln of 3, I suspect some people will forget that there is the log property that difference of two logs is going to be related to quotient, right? Quotient inside of the log. So you could you can end up rewriting this as 80 and then plus 100 ln of, and then 5 over 3. Right? And so that's what the one of the log properties is going to give us. And then lastly, why not simplify that just a little bit more? Right? That 1/2 is not necessary. So ln of 5 over 3, and there we go. So this is probably this is the simplest form you could write this in terms of, and you know, this is actually a word problem, so we should put some units down. This is supposed to denote the average velocity. So we know that this is going to be in terms of miles per hour. Okay. Right. And if you wanted to, you could also figure out what the decimal value for that is. I didn't bother to do that. All right. And lastly, we have number 8. So part A is to just calculate this thing. It's fine. Part B is going to be to interpret, which is maybe a bit harder to see. But yeah, so let's compute this guy. M minus V, we see that there's going to be a simplification here when you subtract. You're going to have a 10t. You'll have a plus sine pi t, but then you have a minus cosine of pi t. And we're integrating with respect to t. Okay. Well, go ahead and integrate this. So this is going to be 5t squared. And now these two terms, well, sine and cosine you can just integrate, but they do have an inner function of pi t. So this is also where like technically it's a u sub, but it's so simple of a u sub that you can avoid the u sub by just doing like a guess and adjust kind of thing. So sine, you know, the integral is going to be cosine, and you would think that it's going to be cosine of pi t, and then you just adjust it from here. So thinking about the derivative of this guy, the sine pi t is going to show up. That's fine. But the chain rule is going to say that pi is going to pop out, and we need to cancel that pi that pops out. Well, how do we do that? We divide by pi. Okay, so now that the pi that comes from chain rule, that gets canceled away. And so this derivative of this is going to be that. And so everything is good. And same thing for the cosine. So integral of the cosine is going to be sine, and give myself space, is going to give. So you would guess this, and you'd adjust because chain rule is going to pop pi out again. So there we go. That's the antiderivative. And now we just need to evaluate this. Okay, so 5 is going to be multiplied by 25. Write that a little bit better. When I plug in 5 to this, cosine of 5 pi is going to be -1. So we end up with plus 1 over pi. Sine of 5 pi is going to be 0, which I will just write. And then we subtract off the evaluation of 2. So, okay. 5 times 4. Plugging in 2 to this, that's going to be 1, so you get -1 over pi, and sine of 2 pi is 0, so maybe put it plus 0 again. And so this is going to be 5 times 21 plus 2 over pi. And so this is 105 plus 2 over pi. And the units for this are meters. Since the thing inside is it's velocity minus velocity, so it's still velocity, and then you're integrating the time away, so that's going to cancel the division by time, so you end up with meters. So you can kind of reason this through unit-wise. Okay. Now for interpreting what this what is this integral actually measuring, right? Well, these individual differences are measuring, I guess, the difference in position from Marie to Fred. And the thing is that when you're integrating over time, it's like you're comparing the two different endpoints in time. So integrating from 2 to 5 is like you're comparing the state of things at the 2-minute mark versus at the 5-minute mark. And then, well, So what is this integral going to end up measuring? It's measuring the change in distance that happens. So it's like first, say Maria is like ahead by 5 meters, and then at the 5 minute mark, she's ahead or behind, but like something has changed in the state of things. The difference, the net change, is what the integral is measuring. So I'll write it. I would write it like this. So this integral is measuring the net change in distance between the two people, Mary and Fred. And then to be even more precise, you should specify the times that we're comparing. So from the minute 2 to minute 5. Okay. All right. So yeah, that's the end of the problem set. Are there any questions that you have? Well, so I'm not hearing any questions. I guess I'll stop